What if I told you that the entire future of technology, we're talking AI, robotics, self-driving cars, all of it, is being held back by one single bottleneck? And what if a group of companies was planning to build a factory so ridiculously enormous it could solve that problem all at once? Well, this is the story of the Terafab, and it's one of the most audacious industrial plans ever dreamed up.
Okay, this single statement is the key to understanding literally everything we're about to talk about. It basically claims that the entire world's capacity to make advanced computer chips is just a tiny drop in the ocean compared to what companies like Tesla, SpaceX, and XAI are going to need. This isn't just some supply chain headache. For companies whose entire future is built on AI, it's a fundamental brick wall standing in the way of progress.
All right, so let's start right there with that core problem. The incredible pace of AI, of self-driving cars, and humanoid robots. It's creating this absolutely insatiable hunger for processing power. And right now, all that incredible progress is being throttled by one single thing: a massive and still growing shortage of computing power.
I mean, that 2% figure, it's just staggering when you really think about it. It means that even if these companies could somehow buy every single advanced chip made on the entire planet, it would only get them a tiny fraction of what they need. So what do you do when you can't buy the tools to build the future? Well, you've got to build them yourself, and on a scale that nobody has ever even imagined.
And that, right there, brings us to the proposed solution, the Terafab. This is a truly radical attempt to vertically integrate semiconductor manufacturing, which is just about the most complex and expensive industrial process on Earth, and do it at a scale that could honestly reshape the entire tech industry. It's a massive bet, and it's all built on a really unique collaboration.
So here's how it's all structured. It's a joint venture, a team-up, between three companies that are separate, but, very interconnected. Tesla brings the huge demand. They need chips for their cars and the Optimus robot. SpaceX, of course, provides the rockets and all the logistics for getting stuff into orbit. And XAI drives the actual AI software and training. This setup creates this incredibly powerful closed-loop system where chips can be designed, built, and then tested in their real-world products almost instantly.
And the sheer physical size of this thing, it's honestly hard to wrap your head around. The proposed factory down in Austin, Texas is planned to be 100 million square feet. That is 15 times the size of the Pentagon. We're talking about an industrial site on a scale that's, well, it's almost unimaginable.
So what kind of factory are we actually talking about here? Well, it's targeting the absolute cutting edge, the 2-nanometer process, using advanced technology from Intel. The initial price tag? A cool $20 to $25 billion. And the power it needs? Over 10 gigawatts. That's enough to power a small country. The whole point of all this is to eventually produce a terawatt of compute, which is a staggering 50 times the entire world's current AI capacity. Just let that sink in for a moment.
But look, this isn't just about building big, it's about building fast. The Terafab plans to completely revolutionize how chips are made, borrowing a manufacturing playbook right from Tesla's car factories to hit what you might call ludicrous speed and efficiency.
And that playbook is what's known as the unboxed philosophy. So instead of a slow, single-file production line, you basically break the factory up into all these self-contained parallel modules that work at the same time. Traditional chip fabs can have months of delay between a design change and a finished product. The unboxed method aims to shrink that entire design-to-test cycle down to just a matter of days. So here's what that looks like in practice. It all starts with the design, done right there in-house. Then, instead of that long assembly line, wafers get made in these self-contained modular cells. They get packaged up using really advanced 3D stacking. But here's the real game changer. The final step is a closed feedback loop. That means new chips can be put into cars and robots and tested almost immediately. This isn't just a small improvement. The goal here is to out-iterate the rest of the industry by a factor of 10.
So what is this factory actually going to make? Well, it's really two main families of chips. On one side, you've got the AI5 and AI6 chips. These are for Earth. They're designed for low-power, super-efficient performance, thanks Cybercab and the Optimus robot. But on the other side, you have the D3 chip, and that is a totally different beast, built to be radiation-hardened and tough enough for the extreme environment of space.
And this is where the plan goes from just being ambitious to something truly radical. Because get this, 80% of the Terafab's massive output isn't even meant for use on Earth. The ultimate plan is to move the data centers themselves into orbit.
Which, raises a pretty huge question, right? If you're building the world's biggest chip factory, why is it still not enough? Why go through all the immense complexity and expense of putting data centers in space? Well, the answer comes down to fundamental physics.
See, down here on Earth, when you try to build these giant AI data centers, you just run into hard limits, real physical walls. You're constrained by land, by water for cooling, and you totally overwhelm the power grids. Space, on the other hand, has none of those problems. You've got unlimited room, constant solar power, and the most effective cooling system imaginable, the infinite cold vacuum of space.
And the energy advantage up there, it's just dramatic. A solar panel in orbit, with no atmosphere, no weather, no day-night cycle, can capture 5 to 8 times more energy than the exact same panel sitting on the ground. That completely changes the economics of how you power these massive supercomputers.
So the vision is a constellation of up to 1 million of these AI sat minis. Each one is basically its own powerful 100 kilowatt orbital data center. And they're all linked together with the same laser technology that powers Starlink. So they wouldn't just be individual satellites, they would form a single global mesh of compute power, kind of like a giant brain in the sky, accessible from anywhere on Earth.
Okay. Deep breath. Let's bring this all back down to Earth for a reality check. Because this isn't just an engineering challenge, it is an absolutely enormous financial and technical gamble.
That $25 billion for the initial factory? Think of it as just the down payment. Some analysts estimate that to actually achieve the full orbital goal, the total investment could reach a mind-boggling $13 trillion over the next decade. To put that into perspective, that's more than half the entire US economy. It's a truly staggering number.
And as you can probably guess, the skepticism from the rest of the industry is intense. This quote from NVIDIA's CEO, Jensen Huang, really captures the bear case perfectly. The world's leading chipmakers have spent decades and hundreds of billions of dollars perfecting this craft. The idea that a newcomer can just waltz in and beat them at their own game is, to many people, just unthinkable.
And the hurdles are just immense. I mean, first you need these hyper-specialized EUV machines to make 2-nanometer chips, and only one company in the world, ASML, makes them. Second, you have to solve the yield problem, which is a fancy way of saying it's notoriously difficult to get enough working chips off each silicon wafer. Then in space, you have to figure out how to radiate 100 kilowatts of waste heat from every single satellite. And of course, there's the money. Raising the tens of billions more needed just to get started is a monumental challenge all by itself.
So it's no surprise that the market is deeply divided. On one side, you've got the bulls, who see this as the foundation for an AI powerhouse that's going to dominate the 21st century. But on the other side, you've got the bears, who see it as a desperate story, a big gamble to distract from declining margins in the car business.
So that's really the central question we're left with. Is the Terafab a logical, even necessary, step towards a future of AI-driven abundance for everyone? Or is it simply the most ambitious and maybe the riskiest industrial gamble ever taken? The answer to that question will probably define the technological landscape for decades to come.